Hi, my name is Sam DeLap, and today I'll be talking to you about moving morphology, using AI for high-throughput musculoskeletal motion reconstruction. Biomechanists study problems related to movement, like how does ACL reconstruction affect the way the knee joint moves? To investigate questions like these, they need to be able to collect precise and accurate data about the joint angle and muscle tendon length and velocity for all of the musculature surrounding the knee. And importantly, they need this data to be three-dimensional to account for all the different ways that the knee can move. One way that biomechanists can collect this data is by placing markers at key bone and joint locations and capturing two planes of X-ray video, with the goal of combining the marker movement with a bone model to create a three-dimensional reconstruction of the movement. So let's say that instead of ACL reconstruction, you're interested, like we are in the Konow lab, in studying how salamanders, like the ones shown in these X-ray images with the head here and here, change the way they chew based on the food they eat. So you find 3 different food types and you want to collect 10 trials for each of them. Congratulations, you've just signed up for a combined 63,000 frames of video analysis across which you'll track around 1.26 million marker locations. On average, this will take you somewhere between 5 weeks if you're an experienced research active professor who's willing to do nothing but track markers during the week, and 32 weeks if you're an inexperienced student researcher trying to balance working in a lab with your normal course load. All told, you'll spend somewhere between 180 and 320 hours tracking these markers, which is simply far too much time tracking markers. Enter DeLap Cut, an AI marker tracking framework that was designed to track markers so that you don't have to. Combined with the XROMM DLC tools package, DeLap Cut produced similar results to human tracking in terms of reprojection error, which is a metric that we can use to determine how good our tracking is. As you can see with the AI data on the left and the human data on the right, the AI data is still slightly worse at tracking markers than human, but it can do it in a lot less time. However, the software still isn't perfect. For our chewing data, which at this point spans several species, DeLap Cut was able to track most beads with less than 1 pixel of reprojection error. However, anything that had above 1 pixel of error is unusable for building 3D models, which means that for 3 out of our 4 trials, we wouldn't be able to use the DeLap Cut framework by itself. To fix this, we added a post-processing step to DeLap Cut that filtered out background noise in the image and found the outline of the marker so that we could find its exact center more precisely. Using this post-processing step, we were able to bring almost all of our data under the usable threshold for marker tracking, as shown by the green box plots in this graph. Here you can see the same frame before and after going through the post-processing step. Even visually, markers are much closer to the beads that they represent after the post-processing step. In our preliminary testing, we've seen that using these AI tools reduces the time spent tracking markers by 80%. For our example study with our example student, this takes the 6 months that they would have spent tracking markers and turns it into just 6 weeks. As we close, I'd like to thank the Konow Lab for their support and input on this project, and Dr. Andrew Buhner on the Concord Field Station for allowing us to use their X-ray rig. This work would not be possible without you. Thanks so much for listening, and take care.